like to do today is finish up what I started last time. So far, Jim Blinn and I have been going like this. Keep you on your toes. We'll do a little bit of a merge today because we'll talk about surfaces and how to display them. All right, first of all, to finish off the hardware, we didn't get to talk about video recorders. It is not easy to do recording of graphics, single frame recording on the video recorders, but it can be done. The problem is that the videotape recorders are hard on the tape. It is, after all, a mechanical device, and the tape is going back and forth. As I said, it has been done, but you must use caution if you're in a position to do that. The new standards for tape are centering around the 1-inch machines. ABC, for instance, has made a commitment to convert over entirely to a 1-inch machine. In fact, I think it's already happened. Those machines are very good. They're not costing less money than the 2-inch machines, like $60,000 or $70,000 each. They're kinder to tape than the old 2-inch machines were. There are video discs, analog video discs, which one can use for single frame recording. For instance, most of the sports slow motion that you see is on a device called the HS100. There's a nice, very shiny, silver-looking disc, iridium or something like that. And it's got the head flowing off the surface an order of magnitude closer than on regular magnetic discs. They crash very easily, and they require a full-time engineer to watch them. But on the other hand, they're sort of rugged because they are carting these things around to the football games. It's a little better with games because the head is constantly recording, and as soon as they like something, they'll do this instant playback. If you're doing single frame recording, then while you're getting the next frame ready, the head is waiting for you to lay down that frame. Well, the head is so close that it heats the disc up. All right, and the tolerances are so great that if you leave it in one place, it will crash the disc. All right, not from dirt, but the fact that the air will cause it to heat up, and then it deforms a little bit, and the head hits it, and that's all over. The marvels of engineering. And therefore,
you lose a really whole lot by going to film first and then going to videotape. Because you don't have the problem with film.
Well, it can be done that way, but in fact, it means you have a film recorder. The whole notion is that it's sometimes it may be easier to have access to a video machine. These are the trade-offs you've got to make. With video, you can then see what you've got right away. You don't have to develop anything. If you keep the head sweeping on the video discs, then you don't have the problem. But on the other hand, if you want to record the frame, you've got to wait a few seconds. But if you have to wait a few seconds, that's no different than using a tape recorder where you've got to cue up the tape and bring it up to speed and record. It is not very good. It's not a good situation. There is something else coming along, and that's the optical video discs. As you already know, there are Philips and Discovision. They already have discs. They cost things for the home plays are $6 or $7 for the commercial versions. They're $3,000. The problem is the creation of the discs. If you want to make a half-hour disc, then it costs you $2,500 to master it, and then $15 a copy, something like that. The mastering costs almost as much as a commercial player. The companies, each of the companies involved, though, is working on a writable disc, a write-once disc. And the chances are that that may be under $100,000. There are more companies who are working on those optical discs to use them for digital storage. There are already units where they put 10 to the 10th bits on a disk, which is roughly in the order of what the highest density magnetic disks are. And the feeling is they'll be able to get 10 to the 11th, and that's when it becomes interesting. If you're going to write one disk, you'd at least like to be able to put more on it. Okay, that's it for hardware. Any hardware that I didn't cover that you wanted to know about? We're going to be breaking the classes. I may have gotten discombobulated and dropped something out. Okay, let's move on to compensation. Now, for compensation, we're going to create a physical model. The issue we're directing is writing on the film in particular, or slightly more general than that. We have generated an image in the computer, with our model. We want to put it on film, and we want it to be as accurate as possible. The model we're going to construct is with some Polaroid print film, the sort of black and white 4x5 film. You put in, you pull it out, and you squeeze it apart after a minute, or you pull it apart after a minute. We're going to take one of these pieces of paper, and we're going to take actually two pieces of film. One of them is unexposed, and therefore it is black. And the other piece is grossly overexposed, and therefore it is white. And what we're going to do is we're going to take the black piece of paper, and we're going to lay up, we're going to cut a white piece of paper, just cut it right out, and we're going to paste it down onto the black one. And now we're going to consider some little square, let me blow this up now, on a piece of paper. So this is our square, and let's say the line passes through it, something like this. And we'll measure our square such that we'll call this distance of 1, so unit distance. So the area of the square is 1. We may even call the square pixel, just so you can see where we're heading. Now, as we shine light on this square, it reflects, the film reflects some of the light. Well, let's suppose that we had all black. That is, the square didn't have a line past through it, it's all black. It still is going to reflect some light. Well, let us call that R min, minimum reflectance. Now let's suppose that the whole square were white. Now it reflects more, we're white. Now it reflects more light. It does not reflect all the light. It reflects maybe 70%. So we'll call that R max. And these numbers are between 0 and 1. R min is not quite 0. R max is 70%, depending upon what the film is. The same argument would also apply if we were dealing with transparencies, and instead of reflectance, we talk about transmittance. It'll transmit all of the light or none of the light. It's again a number between 0 and 1.
How close to 0 does R min get?
Well, let me think. I don't recall if it moved 0.01 or something like that. That's too rough. Don't count on what I said, but it's because normally when we deal with the numbers, we're dealing in density terms. And, I don't recall what the actual reflectance is. For a really good transparency, the typical transparency, the ratio of these two is about 1,000 to 1. And for Polaroid, I'm guessing maybe it's 250 to 1, something in that order. You just divide one by the other. Now, no matter how we construct our line in here, we know that the amount of light that's going to be reflected is somewhere between R min and R max. Now let us step back from our photograph, in that little tiny pixel quite a ways, far enough that it's so small that we are unable to distinguish the internal structure of our little square. It's too detailed. Now, at that point, we still see something, even though we can't see the internal structure. We still see this light that's reflected. That light still falls back on our retina. However, because the structure is too small, it wouldn't really matter if this white and black were replaced by something that was gray, as long as it reflected the same amount of light. Now, let's even go a step further. Let us generate this pixel with the computer. Now, if we're generating with the computer, then what we're talking about, of course, is that we're photographing an image off the CRT, or however we get the image, and some dot on the CRT is going to expose here, and it's going to expose here. Now, in the case of the CRT, we're talking about the resolution of the CRT, and therefore there is no finer structure, period. If you want to put finer structure, then talking about higher resolution. You just change the problem to different magnitude. But if you talk about the resolution you're dealing with, there is no better structure. And therefore, we can only put up a gray value, which we hope would represent what the model says it should be in our computer. Now, let's suppose that for some reason that the film is nonlinear in its response to light. Well, this photograph and that dot there, it puts a gray up there, but it puts up the wrong gray. It's a little too dark or a little too light. Then the result is this line at that pixel will appear either a little bit too thin or a little too fat. Now, if we consider an edge in the picture, let me draw a narrow edge. Let's see, this is a scan line. The individual pixels, here's the line going through it. At the point right here where we're saying there's no light in here, and we don't put anything on, then it's fairly accurate. We get what we expect to get. And down here, when the thing is fully exposed, we get what we want. But if film is nonlinear, then somewhere in here we may find that we get a little bit too little light and a little bit too much light. And the result is, when you look at the image, since you of course can't see the other structure here, you're just seeing the gray thing, you step back and look at it, it looks like it's got a slightly scalloped edge. Therefore, even if you have done all this marvelous anti-aliasing, you find much to your horror that you still have got these artifacts along the edge. All right, let's see, what are the sources of this error? I guess I should draw a couple of curves first. Incidentally, I think this paper is duplicated in one of the books, in the textbook. I'm pretty sure. Am I right? I'm not positive. Does anybody have that book? The tutorial, Kellogg's tutorial. Kellogg's tutorial, that sounds like a cereal. Nobody's got the book. Do we have a book here? It's in the bookstore?
Yeah.
For how much? I don't get a cent.
My friend's book. I thought you were going to get it for us cheap.
$35. Didn't we kick Jim Blinn about it recently? I keep forgetting. Right.
He said that if you're really dedicated, you should be willing to spend the money. Well, he hasn't.
Yeah.
You can get it through the IEEE publication service for 28 plus 6% for sales tax.
Oh man, what are these people getting? 45.
It's only money. All right, so if we draw a little chart here, then this is, let me make sure I'm doing this. We could call area, that's really like our intensity number. And then we've got reflectance. So we've got Rmin, and then Rmax. And we would like it so that, well, if this is our pixel, then as we start to fill it with white, that we've got this linear relationship between the area going from 0 to 1 and the reflectance going from Rmin to Rmax. That's what we'd like. Now, in fact, none of this is linear, and it's not linear for a couple of reasons. One of them is if you have an intensity modulated display, the amount of light that is generated at the phosphor is related to the intensity of the beam by a power law. So it's something like the light given off from the screen is equal to some constant times the intensity of the beam raised to gamma. All right. So that generates some nonlinearity. The second one is the film doesn't respond to light. Let's see, is that the same one we got here? Yes, it is. Some of you may be familiar with the D log E curve, which is the density and then the log of the exposure. And it looks something like this. All right, what that means is, as you put on a little bit of light on the film, well, first of all, if there's no light on the film, there's still some density in the negative. You know it's something. And now you put on a little bit of light, nothing happens. Right? In other words, that's already coming from nonlinear right there, right? You put in some light, nothing happens. Put a little bit more and it starts to happen. Then there's a period in which it behaves sort of linearly. That is, as you increase it, the density changes. And then, as the film gets exposed and you add more light, at some point you're saturated, and then you can put all the light you want, and you aren't going to change what happens in the film. In fact, there's some films, if you go out far enough, it starts to dip back down again.
All of them.
Yeah. Well, no. Reciprocity failure is something else. Reciprocity says you can trade off time with f-stop, and that doesn't work under extreme, very fast speeds or very slow speeds. In fact, Kodak was doing some tests for us on the laser stuff. They didn't have the equipment to do the tests. They just plain didn't know what happened if you put up an intense beam of light for 50 nanoseconds. All right. They didn't know what was going to happen in the film. We think it's going to work. All right. So that's the second thing of intensity. Now, what you can do is since we're using a computer, is do some pre-distortion. Well, actually, let me go over the other linearities. These are other bad things that can happen. On the CRT, you've got this electron beam coming out, hits the face of the CRT, and the electrons bounce off. And so here's this beam, and there's this nice little bright ring around it. All right. What that does is it cuts down the contrast ratio. There's also ambient light within the CRT and in your camera encasing. Another bad thing that can happen is color crosstalk. If you look at the dyes of the film, they overlap. And plus you've got well, I'm not saying this right. You've got this white light coming off of the CRT, and it goes through a filter. Well, the filter's only going to let through light that's, say, here, if it's the red filter. But it turns out this will expose a little bit the green, or the color crosstalk. An example of this is if you grossly overexpose something in blue, and there's a real gross overexposed, it turns white. because the red and the green also get exposed. It's just that it takes longer for that to happen. So these are all bad things that can happen to your picture in the way. We're trying to address mainly the problem of the nonlinearities from the CRT and from the film, because we can take care of those problems. The color is something else to be taken care of, and I don't know if Albie talked about that or not. It's a trickier problem, though. In any case, the notion is that we have got a thing called the color table, or the intensity map. Some different manufacturers have different names for it, but it's a hardware table. You load values into this, and usually there are 256 entries in this table, or it's an 8-bit table. What you'd like to have on the output are at least 10 bits. It'd be nice to have 12 bits coming out. So if you put in a table to compensate for the gamma, that is, let's see, a linear table, when it doesn't do anything, means if you put in a 0, you get a 0 out. So you're going 0 to 512, 511, and 0 to 4095, as an example. A linear table means you put this in and it goes up. If you put in a gamma, which means you're compensating for what that CRT does, then you're taking this to the square root or cube root, or in fact, for television, it probably is 2.3. That is, that's what gamma is, so it's 1 over 2.3. And for high precision CRTs, it's frequently 1 over 3, which gives you a curve looking something like this. Or is it like this? I can never remember which. You got to fool around with it. Find out which way it is. I do have a right in here. Yeah, in fact, I've got a program written in here to do this. All right, so that takes care of one compensation, but you can see that you could have any kind of compensation here. We can combine the different compensations, because now we've got to put the film on top of it. So let's assume we've done the gamma, and now let's worry about the film. Now, if we look at a table of the film...
Hold on a second.
Yes.
So what you're doing is you're going to make 3 passes over the film, or what? To do each of the colors, or?
It's a separate issue. If you want to do color film, then you make 3 passes, or you use a color CRT.
What are we talking about, black and white now?
We're talking, you can think of it as individual components. We're talking about black and white, but you can do the same thing for red and green and blue.
Then you have to worry about the crosstalk.
No. No, the compensation is independent of the crosstalk. The crosstalk is just another bad thing that can happen to you. But with compensation, we're going to come up with a table, and the table will be the same for red and green and blue. And the reason we have confidence that the table is the same for both is that if you load each table with a linear ramp going from black to white, so you got from 0 to full intensity for each color. So we're not worried about linearity, and we're just going to display this, and then we're going to put a ramp, that is, we're going from black to this side all the way up to full exposed. So it's white at this end, black at that end. Now, if we find that we go from black to white, and we go through grays, then if we predistort any one of the colors to compensate for linearities, then we know that we need to compensate the others equally. Otherwise, we wouldn't have gray. Because if we didn't change red the same as we did green and blue, then it would be like moving one of them here and not the other. We already know that equal values gives us gray, and therefore we've got to be the same table. Follow that? Good. A bunch of heads nod.
I want to make sure I understand what you're saying. Is we've computed the color, and we're going to put it out, except that now we'd like to make it a little bit better. So we have a post filter, which is just going to say, like, well, Polaroid film has this type of distortion. And so the post filter changes the gray values a little bit to compensate for the film, for the Polaroid film. And we might have another type of filter for another type of film which has different characteristics.
Except for one thing. We don't use the word filter in this context. All right. Pardon?
I'm a Unix hacker.
Oh, okay. No, yeah, I understand. But in graphics, filter has another meaning. But that's right. We're adjusting it with this table. Let me try to draw a graph how that happens. And the point of this is we're talking about black and white, but in fact it applies to each of the colors. Therefore, let us forget color and just talk about black and white. Now, if we plot our intensity versus the reflectance off the film, then recall that what we wanted, with our intensity going from 0 to 511, we want our reflectance to go from the min to the max. That's what we want. All right. So let us put down a bunch of little squares of different intensities and plot them and see what happens. Well, typically what happens is you get something that looks like that. It starts at min, ends at max, but it's not linear. All right, what we're going to do is make up a table for compensation. And here's how we're going to do it. Let us pick off a value, say here at 0.6. And we look at our plot, and we say, well, this is what I wanted. What did I get? Well, I got, I don't want to say that this way. This is the value I wanted. How do I get what I want? Well, if I now look over in this table, just over straight, I find that the way I really got that was I had 0.35 as an example. These are, I'm now talking 0 to 1, but they should be scaled to 0 to 511. All right. So that's what I really got. And therefore what I should do is go into this table, which is 0.6, and load in the value 0.35. Now every time that I want to display 0.6, I send 0.6 and it goes off to my table, and now it's sub on hardware. I give it the 0.6 value. Well, in fact, it's being displayed automatically. You're not sending it. It's in the memory. And it's going to the refresh, takes each one of these values in terms, sends it to the memory. If it's 0.6, it sends a 0.35 to display. The 0.35 ends up putting this value. Now, if you had said, okay, I want to see 0.6, and you measure what you got for 0.6, this is the value that gets laid down. And so now if you measure it, you'll find that you get a ramp like that. Follow that? Now, this concept has been known for some time, but there's a rub with the whole darn thing. And that is that the way your eye behaves and the way film behaves is not in some linear fashion, but is in a log mode. All right, that's the first rub. And log is always hard to think in than linear. The way to do that then is instead of doing equal steps, that is you wouldn't plot this thing by taking equal steps in intensity. Instead you would do something at full intensity, 511, and then you'd do one at half intensity, 256, then 128, and it was going down in log steps. In fact, we really put one in here too, to go down in 1 over square root of 2 steps. So we're going in a logarithmic fashion. Then we plot, when we measure the density, and the other thing is that when you measure, you usually don't directly measure the reflectance. You've got densitometers, and densitometers measure density, which are a logarithmic measurement. So you put up a logarithmic curve, you measure this density, and you end up with what you want. Now the next problem is that any data like that has got noise in it. And therefore, people who implement this, and there have not been very many people who have implemented this, have got to worry about least squares fits, and all of a sudden the whole thing starts getting a little bit messy, and therefore people say, oh, the hell with it, I'll just use a linear table. And the pictures don't look right. So the purpose of this is why I wrote this tutorial, in fact, was I wrote a little program, and the whole program is written in what I hope is a readable language. I just made up a language, but we all know what computer languages look like, right? Pardon? Unreadable, right. So the whole thing is there, so that everybody wants to implement it, they can.
Excuse me, where is this tutorial?
It's in the book.
In the color?
Yeah, it was reproduced in there.
Could you hold it up? Because I don't think I've seen it.
Oh, this is just my copy. This is also published in SIGGRAPH.
Could you say the title?
It's a tutorial on compensation tables.
Okay.
And it's in, pardon?
You sure that's in color?
No, that's why I was asking if somebody had it.
Yeah, I don't think it's in color. I think you've got something in there, but it's not bad. It's in the book short without any line.
Oh, he's got a second volume coming in. I bet it's in that one. That's another $35.
40, it's gone up.
And I still don't get anything, except a copy. You should all get copies of past SIGGRAPHs.
What issue is that one in?
2 or 3 years ago. I don't know which issue, to tell the truth. Right. Sorry about that. I assumed it was in the article. Anyway, let's show the 2 slides now. Although the film that we're showing for these slides are in fact a fairly linear film. Polaroid film is much more nonlinear.
That's a good one.
Well, this happens to be 5247, which is normal movie film. Now, what this is the plot of intensity. So here's 255. In fact, I think they're also listed here in the paper. 255 and I forget what the next number is. Measure densities. Okay, here we go. 255. I do go just halfway. 128, 64, 32, 8, 4210. This is a linear. Just every single value is here from 0 to 255, just for reference. The background gray is 14, or 37. It's just meant to be a background gray, a fairly dark gray. Then these are measured one at a time, and when they're measured, the plot is drawn. You say this is one particular film, and you see the linearity. That particular film is not a terribly nonlinear film, although it looks curvier because this is the entire. This is in linear, and it looks curvier if you put in the density. And again, it's in the density what matters more. Okay, so that's the curve we're going to measure to find what the linearities are. Could you show the next slide, please? And that is 2 passes through it. No, I'm lying. I actually showed this 2 in reverse order. It's been a long time since I've gone through this. This is the original one. This is the black and white ramp. And this shows what the color map is. I'm sorry. All right, this is the color map. And then if we go back to the previous slide. So we measured this, and now we fitted it. And this is what the new table looks like. These are the entries in the table. So that's the right order. All right, and that's how it happens. And again, if you look at it in density order, this thing looks funnier. Now, the way I did it was not to do these squares, but to fit it with a B-spline and make 2 passes through it. Okay, can you turn the projector off, please? Okay, any question on that? All right, with that, we will leave that one. And there was a question asked earlier, which I'll just briefly comment on before we launch into
a question about the corrections. I take it usually most of these frame buffers already have whatever corrections to the final line before the D to A for the CRT itself?
Oh, not at all.
Not at all.
No.
Okay. Do you have to fit one of these things for every different film or every different batch of film, or could you, for example, if you had a frame buffer where you can only stick in proms as opposed to a write-only map, how many different sets of proms would you have to sit around?
Well, you should have one for your display, because as I say, your display is roughly a square device. Nobody does that. Nobody. And that's just for your normal display for viewing. You really only need one map if you're just going to be looking at a monitor. If you're going to be recording on film, then every film has its own characteristic curve. All right. Tell you what? It isn't that bad, actually. It isn't that bad. But each film does need it. Yes?
You said that the color tables, that the compensation tables were the same for the three colors or whatever, the emulsion sensitivities you had. I was wondering, there are also, in the emulsion, the different layers are sensitive to in different quantities. Is there a possibility of correcting for that?
Well, yes, there is. And what it amounts to is you've got red, green, blue coming in, and you run it through a 3x3 matrix, and that will compensate for certain kinds of color crosstalk. Let's see, that's one flavor. The other is there's a colorable scheme in 3 dimensions for the thing I just talked about, and Jim Blaine, in fact, worked on it, but it's pretty difficult stuff, and it's not. It's a sort of thing you normally don't have to worry about unless you're really after the super critical good recording. And the person that probably better understands ways of doing this than anybody else is Alvy. Unless you're really interested in going to film, it probably isn't worth spending a lot of time on, because it's pretty hard stuff. All right, now this just a minor thing. A question was asked before about finding the area of a polygon. Let's see, one simple way of doing it is the following. Take a leg at a time of a polygon, and the area of this four-sided thing here is this y plus this y divided by 2 times the base. In other words, let's do this, x0, p0, p1, p2, p3, p4. So if you take, this is the y direction, this is the x direction. If you take y0 plus y1 over 2 times x1 minus x0, then that's the area of this thing, right? And now if you move on to this one, then and you find the area of this thing, then it's y1 plus y2 times x2 minus x1 over 2 plus this one, which is y2 plus y3 times x3 minus x2 over 2 plus, we'll keep on going here, y3 plus y4, why did I have 4 sides instead of a 5-side polygon, times x4 minus x3, and finally we've got y4 plus y0 over 2 times x0 minus x4. Now, if you do that, you get a positive area, a positive area, a positive area. This is a negative area, and this is a negative area. So you've got these positive areas, which you've added up, which is everything from here down, there. And then but you add in negative areas, which is this stuff, and you're left with the area there. Unless you're in the wrong direction, you end up with a total negative area. All right, that's how we do it. That will not correctly well, no, excuse me. You will also correctly find the area of a cross polygon, which might be 0. So you've got to be aware of the fact that if you have a cross polygon, then in fact it may have a 0 area because half of it's negative and half of it's positive. All right, that was just in response to somebody's question. If you do this enough, you build up these little things that you've already thought through, and you don't have to think through them again.
Where does that come up?
Pardon?
Where does that come up?
Oh, so we want to know how to find the area of a polygon for NA-lacing. All right? Next, we're going to talk about B-splines and rendering them. And I was going to launch in how to display a parametric curved surface, and someone said that there are a few things I might want to cover first about B-splines. Typically, we deal with cubic B-splines. And before we talk about surfaces, let's briefly talk about curves. If we have got a cubic curve, then there are 4 pieces of information associated with that curve. And the definition of a curve is something like the following. The x equation, that is x as a function of t, is going to be equal to t cubed, t squared, t1, times a, b, c, d. All right, those are the coefficients. So there's one of these for y, so there's a y of t and a z of t. And the difference is that each one of them has its own set of coefficients. Now, normally, all the way through the process, we treat x, y, and z independently. So let us just, since they're independent, they're all the same, let's just talk about x. But I don't want you to get confused to think that that is the curve. The curve is all 3 of them together. That defines a 3-space curve. So you've got this one curve which may look like this in t, another one which looks like this in t. So this is x, and this is y, and this is z. And the result in space, in 3-dimensional space, is some curve that wanders around like so. But you break it down into these 3 pieces, treat them independently. So let's talk about x. How do we define the curve? We're only interested in finding out what those coefficients are. But if you have got some curve, you don't know ahead of time, a priori, what those coefficients are, and you want some convenient way of doing that. Well, there are a number of convenient ways of determining what the coefficients should be. And they are as follows. One which you've talked about quite a bit is the Bayesian. And the way that works is you have got 4 points. Now, if you've got those 4 points, what you do is you can find the coefficients by plugging the 4 points into a little matrix like this, P3. So those are your 4 numbers. So this is, we've got x1, x2, x3, and x4. Remember, we're doing the same thing for the y's and for the z's. All right, that happens easily. So we've got our x values. In fact, let me apologize. Let me write x1, x2, x3, x4. There's a constant set of coefficients which are used for Bayesian. And that is, do all of you have that from previous lectures? Okay, you should have it. So you plug in that matrix, and what you've got are the coefficients. And that gives you a curve which looks like this. And you know that this curve is tangent to this leg, and tangent to this leg. All right, you all know that, right? So if you want to attach curves together, you just make sure that this point and this point here, see, these 3 points are collinear, and then who cares where the other ones are? All right, that's your next set right there. And that's how you piece them together. If instead of using these 4 points, you would like to use the normal vectors for the curve, then instead of putting in x1, x2, x3, x4, you put in the x1 and x2 and vector 1 and vector 2, which are they're just 4 numbers again. Remember, in all cases, there are 4 numbers. You plug them in there and a different matrix. The same is true with the B-spline. With the B-spline, we've got 4 numbers, and it turns out the numbers we put in here, I just happen to have written down because they're in this little paper I brought with me on the condensation. And this looks like -1, 3, -3, 1, 3, -6, 3, 0, -3, 0, 3, 0, 1, 4, 1, 0. And there's supposed to be a 1/6 in front of this, I think. All right. So there's a 1/6. That's the matrix. Now, if you do that with these 4 points, that's going to generate a curve that goes like that. And now, if I've got another curve here, then we overlap, we just meet over 1 point, and we're going to find a curve that goes like so. Now, the nice thing about the B-spline is that all I have to do is add 1 point, and the new curve that I generated here is connected with this curve with second derivative continuity. So you just flip out these points. Everything's easy. Yes?
What's the right-hand side of the
This?
multiplication? No, what's that equal, that whole thing?
All right? X of t equals that. Then y of t equals, everything is the same except you plug in the y numbers here. And it really is that simple. If you had a CRT in front of you, you could write a simple little program which did this arithmetic, and you would say, all right, t equals 0. So you put t equals 0 into this equation for your first points here. You're in a loop now, all right? We're going to go 10 steps. You start at t equals 0. You plug it in here and you get a coordinate. You position the beam on the screen there. Now you say t equals 0.1, multiply it through, and you get the next point. On up through t equals 10. T equals 10, you've drawn that. You then adjust these points, that is, you put in x5, and so you go x2, x3, x4, x5, and then start back here at t equals 0. Except we'll do the same point twice. You'd probably start at t equals 0.1. All right, and then you draw that nice, beautiful curve out. And that's all there is to it. How got that now? For a surface, it's as easy as long as you understand what the next step is. If you put in any value of t here, so we've got these 4 points here, and they generate a curve that looks like this. We're now using this equation. We put any value of t equals 0, and we end up with a point right there. Now, let's suppose that we have got next door to it. Oh, we're changing it, okay. With Bayesian, you're done with this 4, then you move on to the next 4, except one overlaps, you really grabbed in 3 points. Where the B-spline, you move over 1 at a time instead of 3 at a time. So in any case, let us take an adjoining set of 4 points, like this, and that's going to generate a curve something like this. So what we've got is a similar equation here, except that let us, for convenience, say that we've got another set of x. In fact, let's do this 1, 1, 2, 1, 3, 1, 4, 1. So this is 1, 2, x1, oh boy, I botched this up. Wait a minute. 1, 1, 1, 2, 1, 3, 1, 4, 2, 1, 2, 2, x2, 3, x2, 4. Now, if I have, let's just look at this first one here. If I multiply all this out, I'm going to end up with a new value of x. Let's call it x1 prime. That's right there, that value right there, x1 prime. We take the next set of x's, and we end up with a new value here, which is x2 prime. And obviously, we're going to do the same thing here and here. And so we've got those curves. We're only considering one point here, and these are these primes. We've got an x3 prime, x4 prime, because we have these guys like so. And so what we end up with, after we've done all this, and we've set t equal to 0 in every case, is we have got 4 points here. That's all. So here are our 4 points, just like these points, except these are laid on their side. Well, if they're laid on their side, let's use those 4 points to generate a curve that goes here. And therefore, and I just ran out of board space, we take this matrix, and we multiply it times this and 1/6, and instead of t, we say s down the other side. And that s curve is the one that goes here. Now, as we change t by a very small amount, we see that we're generating curves that sweep slowly across here, and we have made a patch. Now, instead of drawing it this awkward way, what we would do is we would say the x, which is a function of t and s, is equal to the t cubed, t squared, t1, times the magic Bayesian or B-spline matrix, which let's call B, times a 4x4 vector of points, matrix of points, which let's call the points. And so it's 16 points, times, we're now going the other direction here, the transpose of the Bayesian, again, followed by s cubed, s squared, s, and 1. That defines this surface. If I put in any value of t between 0 and 1, any value of s between 0 and 1, then I can get any point on this surface. Now, in this particular case, if I have got another set of 4 points out here, now I overlap these 4 points, and that will generate the curve that goes like this. And I'll have second derivative continuity across there. Now, you don't even have to understand it. You just need to know that you multiply these matrices together, and it works.
Is there a quick way for adding the extra 4 points without having to recompute the transpose?
Without having to, you mean having to redo this multiply?
Yeah, only doing, say, 4 in the column.
Well, I think in the general context of the whole problem, that's not a major issue. That isn't where the time's being spent. There very well may be some games that can be played to do that, but I don't think that they're necessary. Now, there are a few tricks with these surfaces that that you may or may not know about. I don't know how much was covered by Nelson on some of these tricks. If you look at the B-spline, are you familiar with the fact that you can recursively take this net and make it a finer net? You know how to do that? Where you join the midpoints. You know about that? Yeah, I should be looking at John, right?
We did Bezier surfaces, but not B-spline surfaces.
Okay, well, this is Bezier.
Oh, okay, you said that.
I'm sorry, they both start with a B. All right, the reason I'm bringing this up is this will come up later. If you've got your original 4 points with the Bezier, then if you take the midpoint of this leg and the midpoint of this leg and the midpoint of this leg, now you join these two midpoints to find that midpoint, those two to find that midpoint. Now you find the midpoint of this leg, you'll see that you've got these 4, and then overlapping with these 4. Observe that these 3 are collinear, and what you have got now is a Bezier net for this half and a Bezier net for this half. And they are the Bezier nets for those two halves of the curve. But observe that the new finer Bezier net is starting to look a little bit more like the curve that it approximates. And we already know that 3 of the points lie on the curve. And if we did this again, and so, you know, these get joined and these get joined. All right, we can see what's happening. You go through 3 of these iterations, and you converge very rapidly onto the curve itself. And I only went through it 3 times. It's a little rough on the board, of course. But it does happen quickly. So instead of going through all this arithmetic, you have got a new option for you. And that is you take these points and you find the midpoints. And you calculate this finer net. And you do it 3 times, and you didn't need to do all this stuff. Although there are other reasons for doing this and being aware of this. All right, got that? Now the next thing you should know, and this is a little tricky, I'm not going to go into this today, is, as you might suspect, all of these different representations of curves translate into each other. If you have got a B-spline, because B-spline is very convenient to work with. Bezier requires that these things have collinear edges on them, right? Well, that's kind of awkward to work with. I'm sorry, Bezier requires you've got collinear. B-spline doesn't. B-spline says, just give me a rectilinear net, period, and I'll give you a beautiful looking curve. But you've got to solve all this arithmetic with the B-spline, unless you take your coefficients here and you translate them into Bezier coordinates for each individual patch, and then use it. Well, then how do you do that? Let's see.
What's a rectilinear?
Oh, everything is 4-sided. Notice that when I was drawing these patches, it was rectangular, topologically rectangular. Right. In other words, if you just had an arbitrary net where things are connected, none of this stuff works. There are some other ways of doing that, but that's a whole different topic. Let's see. Okay, I won't actually do the conversion now because I would stumble around for a bit trying to rethink how to do it right. I will have to remember to come back and show you how to do the conversion. Okay, so you've all got that. You now have defined some surface, and we're now at the step of wanting to display this parametric surface, or bivariate surface. It's called bivariate because you've got 2 variables. This stuff is also called the tensor product. All right, that's a pretty intimidating name, at least for me. But in fact, it's simple. Once you get this down, you're just plugging numbers into this thing. So now you want to display it. Well, you've been thinking about polygons. Now the polygons are easy to think about because, as we talked about before, they're not well defined. But they do tend to be planar and have straight edges in them. These things are very well defined, but they twist all over the place. In fact, Lauren Carpenter had one patch. It looked like a pinwheel. It was a 4-sided pinwheel. It was really quite amazing, but it really was one patch. Okay. Now, this is what my dissertation work was on, was a way of doing patches. And the concept is really fairly simple. These are the pixels. Let us assume that we have translated our surface into perspective space. Now, that's not really easy to do on itself. If you do translate that surface, then what you end up with is an equation which is x of uv over w of uv and y and z, each of these uv. So instead of having a nice simple equation, cubic equation, which we had drawn on the board before, you've got a rational one. You've got one cubic equation divided by another cubic equation. Well, that is more difficult to think about. However, it turns out that it's really quite reasonable to take the control points and run them through perspective. So now you're just running this list of points through perspective. So they're now correctly placed in the perspective space. And now in the perspective space, after you've done the divide by W, you now create the curve. All right. It is not exactly the same, but it's so close that who cares? Actually, I don't know of anybody that's done it completely right. That may not be true. Some may have done it right. And it'd be reasonable, I suppose, to compare exactly right against that approximation to find out what the difference is.
There's no analytical way of analyzing.
Oh, there is an analytical way, but it's a matter of computation. Clearly, this is a very well-defined surface. So one could do it. To my knowledge, nobody has ever done it both ways.
The error. Compute the error.
To compute, well, yeah, there must be an analytical way, but it'd be better off making a picture both ways and then comparing the picture. Because obviously there is an error, but if you do compute it, what does the error mean? In any case, we now have got this curve in perspective space, and let's say the patch looks like this. Now, before I forget about it, while we've got this curve in perspective space, we actually have got to work with the original curve in three-dimensional space, because this curve is no good for lighting. It's good for positioning and placing, but it's worthless for determining what the intensity is. All right. The notion that I came up with is one that does not work in scanline order. There have since been algorithms that were in scanline order, and Jim Blinn will talk about those. We've got a curve here, and what we do is run a simple test, which is not terribly unlike the notion that Warnock had with his hidden service algorithm. Recall what he said is subdivide the screen up and everything that's on the screen into these boxes, and if it's simple enough, then display it. Well, the notion here is instead of dividing the screen up, we're going to take this one surface and we're going to break it up into fourths. So we just subdivide it, and now we ask of each little square, is it small enough just to cover one pixel? And if it is not small enough, then we display it. At some point, these things get to be small enough that they are the size of you can think of them as little tiny polygons, little four sides. At some point, you can even think of this thing as being linear, unless you've got a bizarre surface. And you should count occasionally on having bizarre surfaces. And that's all there is to it. You just subdivide the thing. Now, the other problem is to subdivide means that you're taking that original equation and you're reformulating it where instead of going from 0 to 1, you're going from 0 to 5 or 0 to 0.5 or 0.5 to 1. Well, the arithmetic for doing that can be very time-consuming. And in fact, the first pictures I did took 45 minutes at 256 resolution. It took a long time. And I just solved the equation to make this happen. The next thing I did was to find for cubic curves an optimal way of subdividing. Now, I just showed you with the Bézier a geometric method for subdividing that curve. That geometric method, of course, applies to a surface as well. There's even a more optimal way of doing it, but it doesn't have the geometric base. And it's probably not worth going into. Most people who ever implement algorithms like this couch it in terms of Bézier surfaces, and then subdivide geometrically. Now, the advantage of that is if you have got some surface which is made up of, let me do something like this. I'm not quite drawing this way I wanted. That's what I get for starting a random order. All right, now, I think I've got 4 by 4. If you subdivide this geometrically, then your 4 corner points are still the same. You're going to end up with a new net that goes something like this. All right, and down to here. All right, so here's this new net. The only places where it actually coincides are on the original 4 corners. But now we've got a new net, and we have got, in fact, some new points which are tied down. Well, it'd be here. And again, this net more closely approximates the surface. And you can recurse on that. Well, once you've got this simple geometric model, you can even look at the 4 corners of this, and you can say, does that cover a pixel? Or you might want to look at one of these small ones here, depending upon what your approach is. And at that point, stop. And again, what you're working with is you're adding up numbers and dividing by 2 or dividing by 4, and that's all you're doing. You don't have a lot of hairy equations. You've just got this geometrical net. It's fairly straightforward. Now, given this, you then, since this is in perspective space, as you're dividing this, you also subdivide another net. It's just another whole set of points. You're doing the same operation in parallel, but the numbers are a little bit different. And that gives you the real object in 3 space. And now you reach the point where you say, well, this is ready for display. Well, what is the normal of the surface? Now you go back and you do your calculations on this surface. What is my normal? I'll take some cross products of edges here to find out what the normal is, and I will use that value for my intensity calculation. And then I'll dot it with the light, and I'll lay this down. And I'll also use this geometric information here perhaps to do anti-aliasing. All right? All straightforward? Now, the rub with this is it does require that you have a frame buffer. And when I implemented it, since I didn't have a frame buffer, I paged the frame buffer in off of disk. And in fact, that worked very well. However, there was always this the feeling that it'd be nice to be able to put this in scanline order for 2 reasons. One is that you might want to mix the notion of doing this with other scanline order algorithms like a polygon sorting algorithm. And in fact, that was done at III, where Jim Blinn implemented an algorithm for doing B-spline surfaces inside of a polygon algorithm. And the other reason is that if you do put it in scanline order, you can have everything on a scanline again available at one time in order to do the anti-aliasing properly. So Jim Blinn came up with a scheme which he'll talk about, and then at Boeing, Lauren Carpenter came up with a scheme for taking this same thing here and managing to have it happen in scanline order. Okay, so I've reached a natural breaking point. Are there any questions on this then?
can you say where you break that hull for the subdivision? It doesn't look like you're. Are you doing a binary breaking of it, or?
Yes. It's always into fourths.
Okay, so you're just doing the same thing you're doing with Bezier hulls.
Yeah, this is a Bezier hull. It's not a B-spline hull. Because you convert B-spline, Bezier to B-spline trivially.
Okay.
It's a matrix multiplier.